Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about causal inference. This episode is based on a tech blog titled Covariate Selection in Causal Inference, Good and Bad Controls, written by the data science team at Booking.com. You can find their link in this episode's description. Throughout this episode, we will explore this topic from both the business and data science angles. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Booking.com is one of the world's leading digital travel companies. It connects millions of travelers with accommodations, flights, and experiences worldwide. With hundreds of millions of users, the company makes countless decisions every day about product features, marketing, and personalization, the kind of decisions that often rely on A/B testing. But not every question can be answered with standard A/B test. Sometimes experiments are too costly, too slow, or simply not feasible because of real-world constraints. Take this example. Suppose the team wants to understand whether encouraging app installs can lead to higher customer lifetime value. It's a crucial question that determines how much the company should invest in app marketing campaigns, and whether those campaigns truly pay off in the long run. Since the question can't easily be answered through standard A/B testing, the team relies on causal inference using observational data to estimate how strongly app installs causally impact lifetime value. The challenge here is that many variables can influence this causal relationship. For example, consider whether a customer is loyal or not. Loyal customers are more likely to install the app and are also more likely to rebook, regardless of whether they have the app installed or not. This overlap makes it difficult to untangle the cause and effect between app installs and lifetime value. In situations like this, deciding which variables to include in the causal analysis becomes critical. Including the wrong variables or omitting the right ones can both introduce bias, leading to incorrect estimates of the causal impact. And ultimately, this could misguide customer decisions that result in either over or under investing in app marketing. Now that we've understood the business problem, let's move to the technical side and see how the team tackled this challenge. In short, the team laid out different types of variables that can appear in causal analysis and ran simulation studies to show how each type can either reduce or introduce bias. Throughout their work, they used the same example we discussed earlier, which is to measure the impact of app installs on customer lifetime value. Assuming we didn't introduce any additional variables in this model, this could be modeled rather simply, by running a regression where app install predicts lifetime value. But in the real world, things aren't that straightforward. There are many other variables, let's call them covariates. Those covariates can influence both the treatment and the outcome, so that the team explored how different types of covariates behave when added to the model, and how each affects the reliability of the causal estimates. The first type of covariate is called a mediator. A mediator lies on the causal path between the treatment and the outcome. For example, app bookings can act as a mediator. The treatment is app install, and the outcome is lifetime value, because installing the app may lead to more app-based bookings, which in turn increase lifetime value. If we include these app bookings as a covariate in the model, then that means both the app install and app bookings will be applied in the regression as independent variables, and the impact of the app installs on lifetime values will appear smaller than it truly is. This is because that part of the effect flows through the app booking. The team's simulation confirms this. When mediators are included, the estimated effect of app installs is underestimated. So, to correctly capture both the direct and indirect effects, mediators like app bookings should not be included in the model. This leads to an important rule of thumb. Only consider pretreatment covariates when adjusting for confounding. In other words, including variables that are measured before the treatment happens, those that might influence the outcome but are not themselves affected by the treatment. The next type of variable is a confounder. A confounder influences both the treatment and the outcome. For instance, customer attributes such as recency, frequency, and monetary values, which often summarized as the RFM, are classic examples here. Customers with higher RFM scores are more likely to install the app and are also likely to have a higher lifetime value, regardless of them using the app or not. If we ignore these confounders and simply compare customer lifetime value between customers who installed the app and those who didn't, we could mistakenly attribute the entire lifetime value difference to app install, when in fact, much of it might come from pre-existing customer behaviors. That is why confounders must always be included in the analysis. Omitting them leads to biased estimates of the treatment effects, something the team also demonstrated clearly in their simulation studies. Besides the mediator and confounder, there are variables that influence only one side of the equation, what the team called treatment-only predictors or outcome-only predictors. These variables affect just the treatment or just the outcome. For instance, app score rank determines how visible the app is shown in the App Store. It influences the likelihood of users installing the app, but has no direct relationship with customer lifetime value. In contrast, Net Promoter Score, or NPS, measures the customer satisfaction and loyalty, which can influence lifetime value but is unrelated to the app install. Through simulation studies, the team found out that including this kind of variables doesn't necessarily change the model's bias, but it does affect its variance. Including the treatment-only predictors, like App Store rank, actually increase the variance. That's because conditioning on App Store rank effectively splits the data into smaller subgroups, and without adding any additional information about the outcome. This reduces the effective sample size of the model, which resulting in increased variance. On the other hand, including outcome-only predictors, like the NPS, can reduce variance. By explaining part of the natural variance in lifetime value, these variables make the model more precise, which leads to smaller standard errors in the estimated effect of app installs. The key takeaway here is that it is generally beneficial to include variables that influence the outcome, even if they don't affect the treatment, but avoid including variables that influence only the treatment, unless they also act as confounders. Finally, we come to another covariance called colliders. Those are variables that are caused by both the treatment and the outcome. Colliders are tricky because including them can introduce what's known as collider bias. Identifying colliders usually requires a perfect causal diagram, which is rarely available in practice. So here, a good guardrail is to focus only on pre-treatment covariates for adjustment. This naturally helps to avoid most colliders. And even if colliders bias exists, the team noted that it is usually quite small unless the collider is very strongly linked to unmeasured confounders. So how can data scientists navigate this maze of variables when building causal models? The team summarized several practical principles that lead to more reliable results. Always include confounders. Those are variables that affect both the treatment and the outcome. And include variables that influence the outcome even if they don't impact the treatment. Avoid variables that influence only the treatment unless they also act as confounders. And finally, but very important, include only pre-treatment covariates to prevent accidentally adding mediators. By following these guidelines, it is more secure that the causal inference model built from observational data can yield more trustworthy and less biased results. Now that we've discussed both the business problem and technical solution, let's wrap it up. In this episode, we explored the importance of covariate selection in causal inference, and how different types of covariates can influence the results. This highlights why careful covariate selection is crucial for generating reliable insights, so that it can enable smarter and more evidence-based business decisions. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.